So I have 2 segments of recording today, right? So okay, just try to make sure we have the thing recorded. Is that this table teach us that we need to find a way to use index or key. The key I was saying that the most commonly used is a email address. So when you apply for a any internet account, they will ask you for that email address, right? So use email address to log in. And a university environment, we use the net ID. The net ID will be your key, and that key I use the term key very loosely, but key usually refer to a column in the database table, right? And that column we call them primary key. And so this primary key in this case can be in the SKU data will be the SKU number. It doesn't say number, it just says SKU there. So that's the SKU. And so that is a problem we try to solve. So this set of table is very commonly seen in our data environment. So somehow when we try to make it useful, efficiency, no redundancy, and reduce error, we need to redesign, rearrange the table in a certain way. And certain way is called structured way of data, and to make it more meaningful. And this table from the service doesn't seem to be having problem, but there is a consistency problem. At the bottom of the slide, you see that to understand there's an R table. Nancy Meyer is assigned to a new some sort of a SKU number, right? So Nancy Meyer, you have 10, 10, 10, 110. That's a SKU managed number. So it seems like the buyer is managed that particular inventory number. But there are also some other problem or kind of interesting pattern you can see. For example, Nancy Meyer seems to be one person, right? But if you look at the college major, seems to be referring to the whatever he or she is majoring. Nancy Meyer has two major, art and information system. So the question is, when you look at the data set, is it does she has two major or one major, the other is wrong, or both, or two major at different time, right? So this data set does not give you that answer, and we have that confusion because a lot of time when we start trying to collect data, we just randomly write some column and just start typing, right? So when we collect this inconsistent data, they're just in there, and we have no way to go back to trace and fix it. A good practice will be, if you use Excel spreadsheet, you put a notes here. Okay, our degree is coming from 1988, and information system degree is coming from 2009. So so also that it's a different time, and she got the two different degree. But not everybody is that careful writing a note, and the notes is not, well, at least in the past, cannot be read by computer. So if you want to process the data set automatically, this is a problematic data. So the question is, well, if we can design again the two table system, Nancy, or in this case the buyer is a table, but when we look at the degree, we try to provide a way that the buyer can have multiple degree. And how do you enter multiple degree? That will be a question. So so try to imagine you want to record multiple degree in the on this particular table for each individual buyer. How are you going to be handled that college major? Right. Any? Create a separate table is actually a good practice. So you create a separate table, but how do you make sure a separate table is linked to the original table? Which one is the primary key in that case? very very good. So some sort of ID, right? Some sort of ID. So in this case, maybe buyer's ID. So we assign buyer an ID. We put buyer ID here, but we don't put a name. And but in another table, we have buyer ID, name, degree. That will be one way to solve it. But is that a good way? Not yet, but we will take a look at how we resolve that problem in normalization. But that's general idea. So we create multiple tables. If you want to use one table, there will be also a way to do it. You can create additional column. Say college major 1, college major 2, college major 3. But the question is how many college major you want to have? 10? If you put 10, most people do not have 10 college major. Then you'll be wasting a lot of this columns. Yeah. If you have only 2, what if somebody has 3 major? You'll be missing that data. Right. So that is also okay. You can use, but like in everyday job, if you create just a temporary use database for your, say, student club, you can do that. But we know that kind of a table has problem. So the good news is if you follow normalization rule using the relational database terminology and follow the rule, you will come up with a set of table that is rational, reasonable, structure, can reduce redundancy, and avoid anomaly. That's the beauty of normalization. That is actually the purpose. Again, can I emphasize more? So it was introduced in 1970 by Dr. Cobb from IBM Engineering, and there's some terminology you need to learn. Basically, it's all called key. We'll see separate slide defining different key and so on and so forth. And this is important. And it's also tied to the topic we'll have next week. Now, before we have this relational database theory, table just created randomly based on the needs. So you want to create, you want to do sales, you want to record sales, you just create a sales table and put on whatever necessary column in there, and you record sales, right? And you want to do inventory, you create the inventory table. People at the beginning does not think the problem of synchronize them together, but later they found out the problem. So one of the idea of a good practice people notice is that database world, right? So this is kind of a philosophy already. So I like philosophy, by the way. I like history of philosophy. So in information system, there are a lot of philosophy in there. Okay, one of the philosophy I learned, because I'm a professor, it's my job to share with you some value that I learned from my life, right? One of the philosophy I learned is that technology world or computer world is a virtual world. Whatever you see in the virtual world is the best way of building a virtual world. The best way, not the only way. The best way of to build a virtual world is make the virtual world as close to the real world as possible. That makes sense. So if you want to create a database, whatever you see in that database should be something you can see in the real world, right? And this idea of computer technology is called representation. So if you think about the thing we do in computer, every entry level computer class will tell you that computer world is created by 0 and 1 digit, just 0 and 1 combination of 0 and 1. And what does 0 and 1 mean? It's a symbol, it's a notation. So different combination represents something. Okay, that word, that representation is important. So you are actually using some digital symbol to represent what? Represent the real world, right? So before we have the 3D technology, virtual reality. If you want to represent the real world, because we don't have virtual reality, right? So you take something that is important from the real world and make them into text and save it. That become the representation. And this process is called you record the important attributes of a particular object in the real world into a digital world. And so the representation in the digital world is a database. Okay, so every database is a representation of the real world stuff. So in this case, earlier we see buyer. Buyer in the real world are some people, right? So when you represent the buyer in a virtual world, you got to make sure that the thing you select to represent called attribute in the real world are important and necessary. So you don't waste space, you don't, that sort of all the criteria we use in database building, right? So so that leads to another important concept. So how do you decide on how many table you want to have, right? Yes, there's some rule in normalization we can follow to generate table, but the other important concept is the best table is matched to one object in the real world, right? So that idea leads to the concept of entity. Right? So the first step in building database is to identify entity in the real world. Arrange the entity into a reasonable set, and these entity will become table in your database. And then you do normalization to make the table more reliable, consistent, and reduce redundancy. Right? So example of an entity including customer, computer, and we will come to entity next week when we do entity relationship diagram, right? So with that idea of entity, attribute, representation, table, that kind of a flying around idea about data, then we can go into the theory of relational database. The theory of relational database start by defining what is a table. So table can no longer become a random table. You cannot randomly define a table. You have to define a table in a certain way so that it does not waste space. So it does not, it can help to eliminate duplication, eliminate data quality problem, right? So these are the definition coming up out of the theory. So relation is a table that is a spatial type of table, has the following characteristic. Row contain data about entity, free to go. I'll just relax. Okay, yeah, good. So yeah, I mean, like I said in my class, just because I like to talk, keep talking, holding my coffee and talk. So these are quite characteristic of a relation. So relation is no longer a regular table. So check out each row contain data of an entity, column contain data attribute. All entity and column are the same kind. Column has a unique name, cell, and so. And we'll check very quickly how these quality look like, right? So when you keep the following those rules, you are maintaining something what we call data integrity. Right? So the data integrity can be maintained. So one of the things that we check, just a simple example. So if you check something like, if you have a column says which year were you born, right? So if you look at the year, it should be 1990, 1991, 92, 2000. I think most of you are born between 1990 and 2000, right? So that should be that. So if you see somebody, the year of birth is 2025. What's wrong with it? The person has not been born yet, but it's in the data. But it could be in the data set because somebody may type in 1915. I mean 2015. He typed 2055, possibly. So that's possible. And when you have a data value that is not in the domain, it's called a domain integrity problem. Right? So 2025 will be out of the domain. Or if you have somebody says weekday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, right? And somebody typing there says wood day or metal day or gold day? Are there a day, a gold day or a wood day or metal day? Monday, Tuesday, Wednesday, Sunday? Actually, there is. There are in Japanese calendar. Monday, Tuesday, Wednesday, Thursday are like wood, water, rock, and fires and stones or something. So that's our Japanese calendar. But that is out of the, it's wrong. It's wrong. It's out of the domain. It's called domain integrity problem, right? We try to avoid. So with that understanding of the table characteristic, we can look at this table. This table is an example of a good relation, right? It's very simple to identify good relation. Relation is a term we use in relational database to actually replace table. So, but later in the book, we will use just table. Assume table is a relation, right? So relation, so the correct way to say that a relation is a special type of table. Every relation is a table, but table has many kind of table. Table may not be a relation. So that hear me say that one. Every relation is a table, but not every table is a relation. A relation is a table, but not every table is a relation. To make you more confused or clear. If you sleep well yesterday, that should be very clear. But this is a good relation. Good relation because there's several simple rule of thumb. First of all, you don't see empty cell. Because empty cell represent waste of space. So nothing empty means it's good. It's good. Second, there's no duplication. Right? So you can search for duplication. Oh, there is a Tom duplicate, but they have different last names, so they are different. So they are not duplication. So it's good. Employee number, each one of them are different, so they're good. So this is a good without duplication. Third, domain integrity. Every column should have the same thing. Email address can have only email address. Phone number can have only phone number. You cannot put email address into phone number, right? So this is a consistent relation. So if you follow enter building your database using this method, the chances are you're going to be having a good consistent data, right? So that is one. Example of a bad table that is not considered a relation. So this is a table very commonly seen in Excel. And the problem with the table is if you look at email address should consist only email address, but you see there are label of fax and home here. Those are not consistent. And because of this, you see a lot of empty cell. So this is a table, but not a relation. So it might be a table in Excel, but not a table in relation. So our job in normalization theory is to find a rule, convert this table into two tables. So we can link different number to your employee information from a separate table. Right? So that's the your thing. Very quickly, the table design should be, we probably will use employee number here and the separate table, and we will move the phone number into a separate table. The separate table, just try to imagine, has three columns. The first column is employee number, because you use the employee number as an index to search. So you want to search for Tom, well, not Tom, Jerry Johnson's phone number. You use 100, search in that another table. So another table has 100, and the second column will be type of number. It could be fax, it could be a mobile, could be a phone, and the third column will be the number. Right, so you have employee number, type of the phone, type of the number, and the number. So for Jerry, you might, or for 100, you might find 3 entry into the new table. 100, the first one is the mobile number. The second one is 100 fax number. The third one is home number, right? So you have that three entry. That will solve the problem. And that is actually, when you are doing that, you're actually doing normalization already, right? So another example, this is a bad relation. You see also that inconsistency in different places and empty cell go very quickly. And this one is an interesting table, right? This table, this relation show up because the needs for record more and more data evolve over time. So in the old day, the data are very simple. Usually would just be like names and phone number, email. But sometimes now we, in this case, say, for example, they put comments in there, right? And a more and more Excel spreadsheet, you can put picture in there. Somebody may ask you to say, okay, maybe I will record a voice recording for each employee, introduce themselves. You have a voice data in there. So the column can save picture and voice data. And now it create a problem. Not everybody has a picture, not everybody has a voice data. So, but this seems to be still required. How do we deal with that? And we create this empty cell and this concept called null, N-U-L-L, null cell. Null is a value. It's not no value, it's a value. No value is a value. So we can see, if we consider no value is a value, and this can be a relation, right? But it's a special relation because you have null value in the table. So it seems to be having redundancy, but it's not, because null is something we want to record in there, right? So a lot of things are definition. You can argue one way or the other. And with that idea, now the text will go on to introduce the foundation of normalization. So the basic idea is that we have to identify called the functional dependency. But before we do that, let me introduce this table. This is also a very important conceptual item to remember. And usually we use them by set. Set, I mean, each row is a set. So in database world, and when you talk to people, you have to be very carefully select what terminology or vocabulary you use. And a lot of practitioners, they are not very strict about the selection of word. Sometimes it will create error, problem, right? The most particular row or thing you try to avoid is the one at the bottom. So in database world, don't use the terminology of file, field, or record, which is very common in the old day, right? So, and usually when we have this thing, this is actually coming from the old idea of file cabinet. If you consider that, okay, if in a MIS department, the secretary or a program director, they keep your student record in paper form, they will build a file cabinet. Each file cabinet has a lot of file. Each file is one student. And within the file, you have a record of something, right? And the record has a field, column and field. And that is the idea coming from a traditional hierarchical database, right? New database, we use either the second row. The second row is very academic. Usually we use the term in university and in the abstract level database design. We use relation, and you just learn relation today. Attribute and tuple. The tuple is kind of like a record. But more commonly, in practice, we use the one on top called table, column, and row. So in the future, don't tell people how many records you have in your database. You have how many rows in your table. That is the correct way to ask, or to the jargon to use. So use row, column, table is probably the best way, because most of the practitioners are using that terminology. Okay. So with that in mind, that we can go into the so-called functional dependency concept. And due to the time concern, I'll go this very quickly. And it's actually very confusing in many ways. But basically what we're saying here is that when you know some information, you can search for other information without confusion. Say, for example, if you know a student ID, you can find student name and student address without any trouble. But if you know a student name, can you find student ID without confusing? It seems to be okay, but the truth is not. What if there are two students with the same name? It's very common to have a same name for two students, right? So that is why my net ID is TWNG22. Why 22? There must be another TWING out there. So I'm ranked number 22 out there, right? So so that is basically the rule is, you know something, you can identify uniquely the other attribute. But if you know something that the reverse is not necessarily true, so you know the name, it's not necessary to know the number, then that's not good. Some example of dependency is showing up here. It's again very confusing, and well, when I was a student, this is a big deal. We were tested in the exam. Most of students will lose point in identify the dependency, but in here, since we are not actually using normalization, we will try to go a little bit quicker. This is an example. Sometimes you cannot identify one column as the determinant, or you can use two column combination of two to determine the other one. Right. So in this case, you have student number, class name to determine a grade. If you have student number only, the student take multiple class, you cannot know a particular grade. So and the reverse is also not true. You know the grade, you know which student get A. Well, there are a lot of students getting A. So knowing the direction of the determinant is important. Why? Because the determinant or the column on the left can be selected as the primary key. Can be selected. The best primary key will be single column, but sometimes you cannot identify single column. You have to use more than one column to identify a unique entity or row in a particular table. All right, so there's some rules here. We'll skip, and some very quickly example, identify functional dependency. So when we say if we know SKU number, which is the first column, it seems like we can, well, it seems like the ID or number usually are good, right? And actually, the ID or number is a concept we will learn called surrogate key. It's a artificial, because it does not exist in nature. So in the real world, there is no SKU. People made up SKU, right? In the real world, a monitor is a monitor. When we assign a number to our monitor, that's artificial, human design, a number for that inventory. So that artificial number is a surrogate key. So that one, you know the SKU number, you know the description, you know the department, you know the buyer, right? So that's pretty much it. But if you know the buyer or department, you do not necessarily know the SKU number. So the reverse is not true. So in this example, very quickly, you identify the dependency. Identify dependency is actually tricky, very tricky. And but for our purpose, we don't really need to be an expert. Next week, I will use one example to show you how this thing is done. But for now, let's just understand, okay, this is dependency. Once we know dependency, then we can identify column and their relationship. And if you identify more than one potential primary key, that will be a problem. And that's what we need to deal with. So the goal now is whenever we try to build a table, we identify entity concept. We identify attribute in that entity to build the initial table. And within the attribute, we select a key as that is a determinant. That is a determinant can have other column has functional dependency on that, and use that determine that key as our primary key. If there are more than one, we call each one of them as candidate key, and we select one candidate key. And these keys are important. These primary key are important because one of the biggest problem in computing at the beginning of our class, we thought about this issue of a large amount of data. Large amount of data, you know, they have so many problems. And one of the problems is when you have a large amount of data, and this is the fundamental in computer science as well. If you have taken, well, I mean, all of you have taken computer programming language, right? So if you recall, what did you do in your programming language, other than just learning the notation? The first assignment is probably bubble sort. That makes sense. Did anybody know how to do a bubble sort? Bubble. That sound ring a bell to you? Bubble sort. So they give you 10 number. Ask you to rank the number from the smaller one to the largest one. That's called sorting, right? So the Excel spreadsheet you can sort simply by clicking a column, and the spreadsheet will sort by alphabetically. Right? Sorting is an important job in data management. How do you sort data? Right? Sort data is not a problem when the data is small, but when the data set becomes big, that is a Q square log 2 difficulty computing problem. Right? And if you remember what you learned in bubble sort, you know that you need 2 loop or 3 loop in order to complete the sorting. It takes a lot of repetition in computing. It wastes a lot of computing power. So it is important. So the primary key becomes important because each primary key is a sorting index. So when you have index, the sorting speed will be very quickly. So instead of sorting find a name, you find a number that is much faster, right? I mean, of course, in human eye, finding name is easier, but for computer, finding an ID number is much faster. So this is a trip. Yes. Yes. From computer's perspective, not from human's perspective. So when the computer sort or try to find something, it's faster for computer to find an ID number than a name, because name is a string variable. String variable is more complicated than the number. So number is much faster. So in the computer world, that is why and in recent day, all the database management system will use a concept called surrogate key. So every time a modern day database try to create a table, it will automatically assign a number for every row. So the computer system can read and sort and do all the things that they wanted. And we use another primary key just for human to understand. So the key has meaning to human, but not so much to the computer. So we identify the primary key only for the understanding, easy to understand for human being. But somewhere in between will be this, a surrogate key. So we always invent some sort of a number to represent the item we try to record. And a lot of time these item has meaning attached to it, right? So some of these ID numbers are just number. Some of them have a combination of letter and number, right? Say for example, if you look at your US dollar, the currency, the bill, the notes, US note, $1, $5, $10. Every bill has a number, and the number start with a letter, right? F something, 10 digits, or G something, right? If you happen to have a dollar, I don't carry cash anymore, but look at your money, right? There's a number, and that F, G, I, those letter before the number has a meaning. Now it represents where the money was printed. It could be in Philadelphia, it could be in Chicago, it could be in Houston. I think there are about 10 Federal Reserve Bank in the US printing money. Right? So if you know that, next time you see, okay, F, and you look up, you know where the money is printed. And when I go to China to teach, I usually carry a lot of $2 bill as gift. And these $2 bills are actually printed in Chicago. So that is a gift I carry. It's cheap. Every gift is only $2 and it's meaningful and it's unique because it's $2, not $1. So you can get a $2 bill from the bank. Right, so this is surrogate key. So with that concept of key, primary key, surrogate key, and next we need to understand how they are represented in the design world when we look at table design. And this is the way we usually, there are several ways we use to represent database or table. One is SQL language, the language we use. The second is this one. This is called a schema language. And here I also want to introduce a couple of terms. One is called schema. So this is schema. And the second one is called semantic. Don't mind them leaving that. I'm used to that already. Right, so schema and the semantic, those are the terminology we usually use. And you will encounter this a lot. So in database world, when people tell you, oh, do you know your schema? So what is your schema? Schema is what you're seeing here. Definition of tables. Definition of table are your schema. Right? It has semantic. Semantic meaning there are meaning to that schema. Right? So you need to be able to read this correctly. And this is called a schema language. It's not SQL language is a schema language, but this is a general schema language your textbook uses. Actually, a lot of people are using it. All capital letter represent table name. Capital letter with lowercase represent name of the column. The column with the underscore represent primary key. The column with italic font style represent foreign key. Let's look at another example. So this example has two schema definition, two table defined in schema language. Department table, employee table. Department table has 3 column. Employee table has 4 column. And the primary key for department is department name. Employee is the employee number. It makes sense because department name is not duplicated. So each one is unique. So you can use name instead of a number. And the department name here is a foreign key used as the index to search which department this employee belongs to. So that is how it, and this italic font style represents this foreign key. So take one primary key, insert into another table, become an index, that's called foreign key, right? So that pretty much define the relational database in general. So with that understanding of the schema language, we can actually just read the schema and do normalization. So normalization we will do next time. And what we will do is I will use the example to go through this table. This table tell you the step and well, actually relationship and how we do to reach a certain form. And in general, we have first normal form, second normal form, third normal form, BC normal form, BCNF, fourth normal form, and fifth normal form, and DKNF normal form. So all these are normal form you can achieve. But in modern day based database design, usually we go to the third normal form or at most fourth normal form, and we'll stop there. We will not do further. And and what people argue that, well, then you sacrifice your integrity or a normal ability to avoid anomaly with, yeah. So normal form here is relationship between the tables. The how you arrange the table. Yeah, so when you arrange the table in a certain way, you will reach the first normal form or second normal form, or and so on and so forth. Right. So this exercise we'll do next Monday, but like I said, well, not next month, next Wednesday. But like I said, you will not be doing the exercise. Just experience. Take a look at what it looked like. Will be good enough, right? And why is this? Because why we are not doing the exercise here? There are the reason I start from the beginning. I talk about the trade-off between efficiency and effectiveness, right? So effectiveness here we mean you can refer to how effectively you save the storage space, how effective you eliminate redundancy. The more redundancy you eliminate, more effective your data table design. Make sense? But the faster your data can be insert, sort, delete, the more efficient the database is. So one is the speed of data. The other is the redundancy, right? And these two concepts doesn't seem to be related, but they are. Usually speed can be generated through redundancy. It sounds like meaningless, but if you think about the following situation, I'll use that as a conclusion for my lecture today. If you think about this, if you are running a fast food store, if running a fast food store, right, and you have to prepare hamburger patties and hamburger bread bun, right? And so the manager is facing every day, how many patty I should get ready? Because you have to thaw them from the batch and get it ready so you can put on the fryer. And how many bread you need to warm. So the idea is if we know how many customers, we just prepare exactly that number. That will be most effective because you don't waste any buns or patty. But you don't. The problem is you don't know how many customers out there is coming to your store today. So what do? You have to prepare extra, right? So when you prepare extra, that concept is what? Redundancy. So when you have extra inventory ready, the serving speed will be fast. You can keep serving. If you do not have extra, the process will slow down because when the customer come in, there's no inventory. You have to go to the fridge or buy the inventory, and then that become very slow. So the extra is usually increasing the flow, increasing the speed. So this principle, redundancy and speed, is a trade-off. Right? This in computer world can be seen in the most common example will be something called a cache. So when you use your cell phone, go to a website, and the website will download pictures and things and so on and so forth. And nowadays, almost everybody know that when you go to a website, they will download the picture on your and keep that picture on your cell phone for a while. Why? Because the second time you visit the same website, and people tend to visit the same website all the time, the picture already downloaded don't need to be downloaded again because download take time, right? So that cache memory will actually speed up the web page display on your cell phone. But what is the problem with cache memory? It will ease up your cell phone valuable storage. So when you use your cell phone for a while, you need to clear the cache. Otherwise, it will be slower. Sometimes it will crash. So that's a trade-off actually in computer world with cache redundancy and speed trade-off. In database, we have the same problem as well. Redundancy can increase the speed of accessing data, but at the same time, it will reduce the some other problem, generate some other problem. The speed of transferring will be slow, and there will be some data integrity problem going on as well. So going through the process, we can eliminate some of the problem. I talk about in terms of cache and speed. Yeah. Complexity is another dimension of the issue that, but not well. This when the normalization actually will increase complexity. It will make the table design very complicated. It will increase complexity. So normalization will increase complexity because the more normal form we go into, the more table we generated, right? So basically the process of normalization is fragment the table. So you have a big table, you slice them into multiple tables to save space. So each table only saves the necessary thing using link to link them together. During the process, you create a complexity. You have so many different tables you have to link together. But the result is you reduce the redundancy. So increase complexity, reduce redundancy. But if you go to the reverse process, you will the reverse process is called denormalization. So we have normalization, we have denormalization. Denormalization process will reduce complexity but introduce redundancy in there. Right? So it depends on how and why you are using the data. We will either do normalization or reverse the process called denormalization. So very quickly, the general rule of thumb is if you want to process operation data, or we call the transaction processing database, TPDS, transaction processing, or TPS, transaction processing system. We use normalized database. Right? If you are using data warehouse or data analytic, anything you want to do, analyzing data, or you want to record historical data, anything you want to do reporting, the reporting system need to be denormalized. So reporting system need to reduce the complexity, and transaction processing system need to increase the complexity to maintain that integrity. When you reduce the complexity, then you introduce error into the data set. Right? So that is a trade-off. So it's all about trade-off between normalized database or denormalized database. So if you are kind of confused already here, let me just make it very simple. If you want to build data warehouse, denormalize. If you want to build a regular database, normalize. Regular database, normalize. Data warehouse, denormalize. That's it. All right. So and you'll read that in textbook as well. And but my lecture part of the class today will stop here. And in the classroom, I'll help you. Now, before I help you here, for those of you who are online, if you have any question about assignment 3 and 4, well, maybe, well, I want to answer question on 5, but 3, mainly 3. If you have a problem in 3, you can stay and raise your hand or open your mic, telling me what you want to do. What? Assignment 5 is new next Monday, I think. Yeah, yeah. Again, well, I should say this because in the first week I mentioned that we have a deadline for the assignment, but let's put it in this way: our assignment, all the assignment does not have a hard deadline, right? So you can always due Monday because our class is Wednesday here. You need to have an opportunity in the class to solve the problem. So if you submit the assignment on Monday due, you submit on Wednesday. Usually I will not be, deduct any point. But if you submit this assignment Sunday, that will be about today, tomorrow, and then you'll get some penalty in there. But the goal is you want to complete all the assignment. Well, the buffer is that due date and the class we have right after due date will be the buffer. Right, so today is the buffer for assignment 3 and 4. Right, so next Wednesday will be the buffer for assignment 5, even though the due date is Monday next week. Okay. So for online, yeah, okay.
I
So
submitted all the assignments, but I found that there is a file format for each of the assignment. May I know what is it exactly? Is
file
it
format, file you should be using the Microsoft Word, isn't it?
Microsoft Word? Okay, we just submitted in the PDF. Will it work?
Yeah, that will work. Yeah, PDF, because in the Canvas system, I can see PDF and Word. Yeah, both of them are fine. Yeah, you can
Okay.
submit PDF.
Okay. So is there any specific file name that we need to use?
No, well,
Okay.
on the assignment page, I recommend you just say assignment 1, 2, 3, but you can use any name as long
Okay.
as you are not copy other students' submission. That
It's okay.
if I see Rahul and submit by Tejas 3, then there must be something wrong. Rahul assignment 3, submitted by Tejasri, and that I will investigate.
Okay.
So yeah.
And all of these PPTs, where we can find these in our modules, because you are sharing it with us, but we don't have it in the soft copies, like in the modules or in the syllabus.
You mean a slide?
Yeah.
The slides is on the learning module. I'm opening up. See, this is the learning module we're looking at. So let me go into the student view.
Mhm.
Right. So this is I think this is the Monday class. Well, it's not your class, but Monday class. So module, if you go in this case, module 2, this is chapter 3 slide. This is the one I opened. Chapter
Oh,
4 slide.
okay,
So
okay.
this is the assignment slide.
Yeah.
And module 3 now you can see the new module. We have chapter 5 slide and chapter 6 slide. So these you can download to your and save it somewhere on your computer. So you don't need to come back to Canvas every time to download it. Yeah.
Okay. Okay. Thanks.
Yeah, I mean, it's recommended because, when you are taking the exam, sometimes you don't need to go back to the quiz. You can just open the slide and get the answer.
Yeah.
Okay.